Good morning. Today we are going to take up some very important results using the concept of substitution. Now, as you would have already observed, we had a long list of integrals which we found by observation using the results of derivatives. But since there is no function whose derivative is either tan x or cot x or sec x or cosec x, we could not find the integral of tan x or cot x or sec x or cosec x. So today what we are going to do is, using the process of substitution, we are going to derive the integrals of each of these four functions, which is tan x, cot x, sec x and cosec x, which could not be found out just by observation as other trigonometric functions. Okay. Now let's first take up integral of tan x dx. Okay. So let I be equal to integral of tan x dx. So as I had already mentioned earlier also, whenever we come across a function whose integral, a trigonometric function whose integral cannot be found out directly, we try to convert it in terms of sine and cos. So let us convert this in terms of sine and cos. What does this become? Sine x over cos x into dx. Now again let's see, this is quotient of two functions. One is sin x and the other one is cos x. Now earlier we had seen that whenever we have such a case, we try to put or substitute one function whose derivative is already available in the main function. Now again there is a confusion. Here derivative of sine is cos, cos is sine, so both are present. Now the question arises, which one do we assume to be t? Now if you put cos x as t, okay, so even though we are getting minus sin x dx as dt, but here sin x is in product with cos x, whereas if we put sin x as t, we will get cos x into dx is dt, though its derivative is present, but here what we observe is cos x comes in product with dx, whereas in this function cos x is in the denominator. So this is not the correct choice. This one is the correct choice, that we will take cos x, we will assume cos x as t, so that the derivative sin x dx gets absorbed in dt. So let's write. So let's start again. We are given I is equal to sin x over cos x dx. Put the denominator cos x as t, we get minus sin x dx is dt, so that I becomes equal to, now here we get minus dt over t, which is equal to minus log t, right? And so plus a constant. Substituting back, we get I is equal to minus log cos x plus a constant. Okay, so this is one result, that is integral of tan x dx is equal to minus log of mod of cos x plus c, but more prevalent is the result where we absorb this minus sign. So if you absorb this minus sign, it will become log of cos x inverse, which is log of 1 upon cos x, which is log of sec x plus c. And so we get a very important result, that integral of tan x dx is equal to log of sec x plus a constant. And how do we get that? Since minus log cos x equal to log of cos x inverse plus c, which is equal to log of 1 upon cos x plus c, which is equal to log of sec x plus c. Okay, now similarly we can get the result for cot x, integral of cot x. The second function is integral of cot x dx. Same way we write it as cos x over sin x into dx. Again we can put any one of these as t, but which one will we use? The one whose derivative comes in product with dx. Now cos x is the derivative of sin x, and so put sin x as t, we get cos x dx as dt, and so I becomes equal to dt over t, which is equal to log of t plus c, which is equal to log of mod sin x plus c, and thus we get integral of cot x dx is equal to log of mod sin x plus c. This is the next result. Now let's come to the third result, which is the integral of sec x dx. Okay, now in case of sec x, what we do is this has to be dealt with in a slightly different manner. So what we do is we multiply and divide by sec x plus tan x. Now here by doing so, we are not changing the function, but we are simply writing it in a form which is suitable to us, because since we are multiplying and dividing by the same function, the function remains the same, because this gets cancelled and you are back to sec x dx. Now when you solve it, we get, let's open it, sec squared x plus sec x tan x whole upon sec x plus tan x into dx. Now let's observe carefully. This is again quotient of two functions. In this, sec squared x is the derivative of tan x, and sec x tan x is the derivative of sec x, and so clearly the numerator is the derivative of the denominator. So we put the denominator as t. We get sec x tan x plus sec squared x whole into dx is dt. Substituting, we get I is equal to numerator becomes dt upon denominator is t, which gives you log of t plus c, and so we get the result as integral of sec x dx is log of modulus of sec x plus tan x plus a constant. On the same lines, we get the fourth result, which is I is equal to cosec x dx. Now in this case, again we proceed the same way as the previous case, that is sec x, but with a slight change, that here we multiply and divide by cosec x minus cot x rather than cosec x plus cot x. So we multiply and divide by cosec x minus cot x dx. So this becomes equal to cosec squared x minus cosec x cot x. Cosec x minus cot x dx. Now again clearly we can see that cosec squared x is the derivative of minus cot x, and minus cosec x cot x is a derivative of cosec x. So clearly the numerator is the derivative of the denominator. So put cosec x minus cot x as t, we get cosec x minus cot x as d, we will get the derivative as minus cosec x cot x plus cosec squared x whole dx is dt, and so I becomes equal to dt over t, which is log t plus c, and thus we get integral of cosec x dx is log of cosec x minus cot x plus c, and this is the fourth important result. So thus we have seen that by using the process of integration we could get four very important results, that is result of integral of tan x, which comes out to be log sec x plus constant, integral of cot x, which comes out to be log sin x, integral of sec x, which comes out to be log of sec x plus tan x, whereas integral of cosec x, which comes out to be log of cosec x minus cot x. Thank you.